guys, like I said, sorry I won't be with you this week, but we are going to be talking about the electron structure of the atom, and we're going to have some really fun activities. Not one next week, and then the week after it's going to be a lot of fire and a lot of glow-in-the-dark type stuff. It'll be really, really fun. Can't wait to start that with you guys. Remember, I'm going to be out all week due to the passing of my father, so I'm going to go over some notes with you and try to take care of that real quick. So chapter 5 is where we're going to be at, talking about electrons and how they move around inside the orbitals. We talked a little bit about atomic structure in the last chapter, where we talked about the different types of models. So we're going to really be focusing on the quantum mechanical model in this chapter, and about the modern model and where those energy levels are, and the clouds and the regions and things that we talked about in the last chapter. All right, so remember, when you're doing your notes, the stuff that is written in yellow, that's what you want to write down in your notes. Okay, so in the 1920s, scientists were convinced, okay, the Bohr model was incorrect. They formulated new and innovative explanations of how electrons were arranged in atoms. If you like lasers and laser pointers, the sci-fi glasses, where you can see at night, the night vision goggles, the video games, all those kinds of technology came from electrons. So initially, that's how they started getting that technology, was through electrons. In 1924, Louis de Broglie proposed an idea that accounted for the fixed energy levels in the Bohr model. So the Bohr model, remember, they talked about was where it was just going in circles. They talked about the electrons would orbit the nucleus like the planets orbit the sun. But later on, they figured out, wait a minute, they're not really just going in a circle. These particles, these electrons, are actually more like waves. And so they're traveling and they're bouncing all over the place, jumping from different energy levels, okay? So they kind of changed the Bohr model after that. So de Broglie predicts that all moving particles have wave-like characteristics. So they're moving like this, like in waves, okay? Not just a circle pattern like Bohr originally thought. Now, after developing his idea, he derived the following equation using Einstein and Planck's equation. So this right here is, I just tell people it's the wavelength symbol, okay? So you can just do an upside down Y, okay? And wavelength is equal to Planck's constant, which is h, divided by the mass of the electron times the velocity of the electron, which a lot of times the velocity is the speed of light, okay? Now, after de Broglie started doing these things, they started talking about different implications that he had for the atomic theory. Okay, he stated that it is impossible to know precisely both the velocity and position of a particle at the same time. His principle also means it's impossible to assign fixed paths for electrons like circular orbits in the Bohr model. So what he's saying is, you can pinpoint the velocity but not the position, or you can pinpoint the position but not the velocity at the same point in time. Okay, you cannot do both. It's impossible to do both. Okay, so the modern model of the atom is based on Schrödinger's mathematical model of waves. His model describes electrons as occupying orbitals, not orbits. So what he's saying is, in this region here, electrons will exist. The darker the region, the more probability of finding an electron somewhere in that location. So you have to look at how dense the cloud is at that time, okay? Now, three-dimensional regions in space where electrons are likely to be found, not a circular pathway. So not just like the planets, not circular there. It's a region, okay? And it's three-dimensional like a sphere, okay? Principal energy level is the orbitals of similar size. So we're going to start talking about the different levels. So an energy level would be a row on the periodic table. So we're going to talk about, as you increase these energy levels, the cloud size is going to be bigger. And part of the reason for that is because as you're getting this cloud size to be bigger, you're getting more electrons. So they're moving around. And what do we know about electrons? They're negatively charged, right? So when you have these particles that are negatively charged, they're not going to be side by side. They're going to push each other out because like charges repel one another. So that's why these regions, these cloud regions, are very large and three-dimensional, because they're pushing away from each other. So if an electron jumps from another energy level, it's going to be pushing that other electron. And so when it comes back down, it's going to emit this light, this quanta of light as it's coming back down. Okay? Now, this probability map for our lowest state of the electron. So a probability map shows where the electron is most likely to be found. The closer the dots, the higher the probability. Okay? So you're going to be doing a lab on the electron probability. So you're going to be dropping marbles at a target, and you're going to be showing the probability of finding an electron in a certain region. And so the target is going to be regions within, or energy levels within an electron. Okay? Now, I'm going to show you some pictures in the next couple slides, and I had you color your periodic table here in a minute, and the periodic table, when you color it, it's going to reference some of these shapes that you're going to see, okay? It won't mean a whole lot to you right now, but I promise you, once we get into electron configuration, it's going to be important. So basically, these four orbitals that I'm going to talk about is where the electrons are located, and it depends on the outermost electrons. Where the last electrons are going to be is where you actually have these orbitals, okay? So this is called the s orbital. It actually just looks like a sphere. It looks like a globe, or looks like a ball, okay? Like a soccer ball, or not really a soccer ball, but like a kickball. So it's a solid ball, sphere, okay? Now, orbitals of similar size exist in the same principal energy level, okay? So basically, n equals 1 through 6. So as you go up from 1 to 6, it's going to get larger in size. There are four general types of orbitals. There is S. So S, like I told you a minute ago, looks like a sphere, okay? P kind of looks like a figure 8 or a dumbbell, you know, like one of those old-timey dumbbells, okay? Or teardrops, two teardrops kind of stuck together. Then you have D orbital, okay? So it kind of looks like a flower. And then you have the F orbital, okay? F orbital is kind of crazy. You are not going to have to draw any of these shapes. You just kind of need to know what they look like. So basically, if I were to ask you a question on a test or something, this would be a sphere, this would be a figure 8 or dumbbell, and this would be more like a flower, like a daisy, okay? I will not ask you the shape of the F because it is kind of obscure and it's hard to identify. Now, what I talked a minute ago about what is the principal energy level. A principal energy level is actually rows on the periodic table. So if you looked at a periodic table, you would see that it goes 1 through 7. Those are energy levels. Those are rows on the periodic table. As you increase the row, the size of the s orbital is actually going to increase, okay? And they're going to get bigger in size, as you can see, okay? The p orbital has 3 different sublevels because there's 3 different directions that the p orbitals can rotate in. You have z, x, and y, okay? And you should be familiar with z from math. P orbitals will overlap with their centers at the nucleus. So when you get to the nucleus here, they actually all overlap right there. There are 5 in the d orbital, okay? And you do not have to know any of those directions. You just have to know that there's 5 different directions that they can exist in. And guess what the F orbital has? 7 different directions. Once again, you are not going to have to know that. You just need to know that there are 7 there. Okay? Now, how are electrons arranged in an atom? We will consider the ground state the most stable arrangement of lowest energy. Okay? Now, this will be the last slide we go over today, because then you're going to color your periodic table. You're going to label your table, and you're going to spend some time doing that. I will have a video that I will give to you to watch so that you know how to color your table. Okay, so the first principal energy is n equals 1, a single s orbital. The second principal energy level is row 2. These are rows on the periodic table. You have a 2s and a 2p. Okay, the third principal energy level, n equals 3, you have 3 orbitals, s, p, and d. And then the fourth principal energy level, you're going to have 4, s, p, d, and f. Like I said before, when I start going over this, it's going to make a whole lot more sense once we start getting into electron configuration, okay? So that's what it's gonna look like. You're gonna actually do your table here in a minute, and we're gonna show how to color that, all right? I'll see you in a minute when I go over electron configuration.